Okay, we are at section 22.3, Coulomb's law. Before we get to the PowerPoint, I'm going to share, I'm going to go back in time. Let's see where, I can't find, oh, there it is. This is the Cavendish experiment. This was, we got this in chapter 13. Cavendish measured the force between two different masses using the a torsion pendulum as shown using masses, and he confirmed Newton's gravitational force equation. G equals m1 m2 divided by the separation distance squared, r squared. So that's the gravitational force. Now let's go to the PowerPoint, and it's very similar to the Cavendish experiment, but this time we're using charges instead of using masses to determine the gravitational effect. We're going to use charge, and you might say, "Oh, well, wait a minute. There's mass on these different charges." Well, the electrostatic force is so much greater than the gravitational force that you can ignore the gravitational force in this particular experiment. So Charles Coulomb, and he invented this torsion balance to measure charge, and so he would charge the articles and measure either their repulsion or their attraction. And this is Charles Coulomb, and he discovered that the electrostatic force, the Coulomb force, is equal to Ke Q1 Q2 over R squared. Well, that looks very similar to the gravitational force. Fg equals G times mass 1, mass 2 divided by their separation distance squared. This is very similar. The electrostatic force, the Coulomb force, is equal to Ke Q1 Q2 over R squared, where Ke is a constant, 8.988 we can use times 10 to the 9th Newton meter squared per Coulomb squared, where Ke is derived, it's gotten by 1 over 4 pi epsilon 0, where epsilon 0 is the permittivity of free space. It's 8.8542 times 10 to the minus 12 Coulomb squared divided by Newton meter squared. The charge, the fundamental charge is 1.60218 times 10 to the minus 19 coulombs. Now that could be positive for a proton and negative for an electron, and we're always going to get multiples of this charge. Now we're not going to, probably won't end up with 2 or 3 of them. We're going to end up with just micro coulombs or nano coulombs. 1 Coulomb charge is a very, very large charge. So the fundamental charge is 1.60218 times 10 to the minus 19 coulombs. Okay, so because of conservation of charge, each electron adds negative charge to the silk, and an equal positive charge is left on the glass rod. So it's quantized, it's in multiples. There's always an n times E, where E is 1.6 times 10 to the minus 19 coulombs. 1 coulomb of charge is approximately 6.24 times 10 to the 18 electrons or protons. So 1 coulomb charge is you've got a lot of electrons or a lot of protons. It's very small when compared with the number of free electrons in 1 cubic centimeter of copper, which is approximately 10 to the 23 free electrons. 1 coulomb is a substantial amount. In typical experiments in which rubber or glass or a glass rod is charged by friction, the net charge is 10 to the minus 6 coulombs. Only a very small fraction of total available charge transferred between the rod rod and the rubbing material. Now let's look at some of these. This is going to be a table that you don't necessarily have to memorize, but you want to be able to access it quickly. The charge and mass of the electron, proton, and neutron. So an electron is 1.6 times 10 to the minus 19 coulombs. A proton is 1.6 times 10 to the minus 19 coulombs. A neutron has no charge. Now, the mass of the electron in kilograms is very small, 9.1094 times 10 to the minus 31 kilograms. Proton and neutron are very close. You'll notice that the neutron is slightly heavier, 1.67262 times 10 to the minus 27 for a proton, 1.6793 times 10 to the minus 27 for a neutron. Let me see where I need to, okay, we'll probably after the quick quiz. Yeah, I think so. Okay, so Coulomb's law in vector form, when the charge, let's see, when the charges are the same sign, the force is repulsive. When the charges are of opposite signs, the force is attractive. And we know from Newton's third law, you're going to have forces in pairs. If you have it in one direction, you have it in the opposite direction. For every reaction, there was an equal and opposite. For every action, there is an equal and opposite reaction. So if you have force 1, 2, you're going to have a force 2, 1 in the opposite direction. If you look at the oppositely charged particles, you have F12 attracting, and you have F21 attracting in the opposite direction. So how do you determine that force? Force 1, 2 is equal to KE Q1, Q2 divided by R squared along the vector R12, which is a unit vector. And if you have multiple charges, then you can calculate the individual charges and just sum them together. It's a superposition of all the forces that are available. Let's see. Okay. So the resultant force is the vector sum of the forces exerted by individual charges. Now let's look at a little quiz. Object A has a charge of 2 microcoulombs, and object B has a charge of 6 microcoulombs. Which statement is true about the electric forces on the objects? Okay, you have A and B. Is the force on AB -3 times the force on BA? And let's go back. Remember Newton's third law. Whenever there is a force, there's a equal and opposite force. So really, this is kind of a no-brainer. You can forget all of these that have a integer in front of them. They're going to be the. Oops, I already answered it, didn't I? I went too far. The FAB equals minus FBA. All the ones that have numbers in front of them, just the fact that the B is 3 times the size of A is immaterial. You calculate the force between them, and whatever FAB is, FBA is in the opposite direction. So even E, which has no integers in front of it, is wrong because they're not both going in the same direction. So FAB is equal to minus FBA. And I think that's it. We'll go on to the next section. I think we're at 22.4 in the next video.